Thank you for being a wonderful, wonderful mentor for all of us. You're gonna talk about historical stuff. I'm just gonna mention a little bit of history that I've observed. So when I first started out as a short URA, well, one of the benefits of being Christian is that he will show you a lot of toys to play with. So I got to play with dragons, so that's a lot of fun. And then I became a short master student. And then Chris showed me how to scheme over designs and coding, and I've been scheming since. And then I became a short PhD student, and then Chris showed me the ropes of basically grading and modeling. Thank you for picking A and D to represent the two generators and B3, because there's an equation in my PhD thesis that spells ADA equals DAD. So it's really cool to have your name as part of the equation in your thesis. And then I grew up to be a short former student of Chris in the past 10, 15 years. Thank you for leading us through this quantum journey. I want to kind of mention one quantum phenomenon that Chris and Tino coined, evanescence. Yeah, I always mix up the word. So this is when you're in a quantum walk, when there's a positive time tau, that the AB entry is 0. Okay. Now, if you're a Chris student, then you learn that it's very important to have examples in mathematics. So I'm going to show you one example of evanescence. So I have 2 kids, and that's why I'm introducing Chris. And after he finds out that my kids like sourdough, then he would give me sourdough to bring home sometimes when I come to visit Waterloo, and he is that type of supervisors. So usually every time when I have sourdough, when I get home, then if you do a measurement before I walk into the house, then you'll see the sourdough with basically probability 1. And then once I got in, then they disappear. So evanescence happened. So I'm going to introduce your talk. So Christopher, what have you done?
Actually, I'm gonna all these people talking saying about these nice things that or in what kind of ways I've influenced them. It's very good of them. I'm glad they're not mentioning the less desirable effects that I've had on them. But anyway, there it is. I decided I'd get my thanks in first because there's always a danger I'll forget at the end. So I start by thanking the staff, Carol and Melissa and Jen, for their help. They always do a lot. And they do it very cheerfully. And they make you feel that they're happy doing it. And of course, I want to thank the organisers, Tino and Ada, and Maria, and Sophia, and Sabrina, and Tina. They've done a fine job. And finally, there's the audience and the other speakers have all done a lot to make this a fun weekend. So thanks very much. And thanks for all the good wishes I've received. Okay, now, well, I'm going to start with a quote from a famous...
Sorry, Sophia said that they can't see the screen again. Maybe I will... So Sabrina, can you please pin?
This is
Yeah, me too. Yeah. Seems like I'm moving it away. Can you see the screen okay? This is okay? Yeah, okay.
That's good, thanks.
Okay, so I'm going to start with a quote from a famous songwriter and mathematician, Tom Lehrer, and you can zoom on that, or also Google on that. He said many years ago that some of you may have run into mathematicians and therefore had occasion to wonder how they got that way.
We're actually disconnected locally now.
Okay, okay. Yeah, so some of you may run, and so in some sense, this talk is an explanation about my particular case. And I thought I'd start. Oh, that's pretty good, I think. That's just my shirt. Okay, so yeah, and so in some sense, I'm addressing this to more recent students so they get some idea of where I came from. So I grew up in a town called Warragul, at the time I grew up was about 6,000 people and probably an equal number of cows. It was a dairying community. And so, you know, actually for some strength, for some strange reason, okay. So that's actually the house that I grew up in. Anyway, I have that. And this is a picture taken from probably 10 or 15 kilometers north of Waterloo. Gives you some idea what the, like I said, it was a small town and the focus was on dairying. And so I grew up there. Now people talk about Australia and they worry about the animals. And what I thought I'd go through and clarify a few things because there are some misconceptions. The first thing, you know, they say, well, there's all these venomous things. Well, I'll say the problem is not so much the spiders. Well, oh, damn, this is a real nuisance. I don't think there's a problem with the connection.
Okay, so it's the Wi-Fi or?
There's no Wi-Fi
It's
involved.
here, right?
It has to be the connection.
Well, I've got another connector.
I have an Apple.
Yeah, well, that's what I'm getting at.
Okay.
Yeah. Yeah, but I'm stupid. Okay, so what I was saying, so the other point I'll say is as far as these venomous things go, none of these things are rare. I've seen all these things, sometimes in significant numbers. So there are spiders, but that's not never been a problem. And snakes, well, people talk about snakes, and this is one I got off the web some years ago. This is somebody's Christmas tree, and before people went into their Christmas tree and discovered there was this tiger snake nestled in their tree. I'm not sure whether it's a new step in evolution. I'm just waiting for people to come to the feathers. I should also add that they're one of the most venomous snakes on the planet. Probably one of the top two anyway. And so interesting Christmas morning. But okay, again, I've seen them, but they've never had any big problems. You go to the beach and you see these. This is a pretty little octopuses. The body's only so big. And they're very cute and they're pretty mild, but it's just a will because they've got a very venomous bite which will kill you in 2 hours. So, okay, they're hard animals. But the thing that used to cause me problems was the birds. Okay, and that's from Hitchcock's film. So I got them in sort of order of terror. The problem is these birds will nest and they're very aggressive about people who they think are too close to their nest. So these are mudlarks, we call them. They're so long and they're a bit thin and they're not, you know, they're more noisy and scary than anything. And then on one occasion, remember I was climbing a tree and unfortunately there was a butcherbird had a nest in there and didn't like me there at all. And this was particularly tricky because you're trying to hang onto the tree with one hand and watch the butcherbird and keep it away from you with the other. And then, well, the ones you'll read about most commonly are the magpies because they're very common. And they like to nest in big trees and so they can see a long way. And if they see anybody coming, they tend to attack. And they tend to wait till you're looking away. They seem to have a fondness for attacking cyclists. Again, I can't see the evolutionary reasons for that. So I have a theory that they're really just doing it because it's fun. And you know, sometimes they fall off and it's sort of quite exciting. But the thing, magpies are about sort of crow size. The ones that used to terrify me, I grew up in a rural area and so there were swamps and things. And we had what we call plovers, which are about the size of a duck. And they would fly straight at you and there'd be 2 of them. So you learn very quickly not to go in that particular area of the swamp if you're going fishing or something, because the plovers were quite uptight about things. Okay, so that was a bit of background. So I'm going to start with my PhD work. I did a master's in group theory. And actually, at the end of that, I was trying to decide what I was going to do, whether group theory or graph theory for PhD. And at the time, it seemed I could either do group theory in Sydney or graph theory in Austria. And that sounded a lot more interesting. And so that's what I chose to do. Although as things turned out, I didn't get to Austria. I ended up spending a year in Syracuse University as my PhD, and so basically did in Melbourne. My supervisor there was Derek Holton, and he got his PhD in McGill. So So, okay, that's not, and so, for my thesis, I was working on K-graphs and some related stuff. Not quite sure how I got into K-graphs because I think originally I was more interested in some, well, questions other than what I'm just about to talk about. The background is that Stroop proved, I think in the 30s now, that every finite group occurs in the automorphism group of a graph. Okay, and there's various extensions to this these days, but so, and he, well, he used K-graphs to do it turns out. So every finite group is the automorphism group of a graph. Well, so the question is, you'd like to understand the relation between the structure of the automorphism group and the structure of the graph. This is telling you, well, this question is not going to get you very far. So the question is only going to make sense if you restrict the way in which the group acts. Okay, so you have to make some assumption about to get a connection. And so the one that came up was read the K-graph. So you have a group G and a subset C. And I'm assuming that this should be C, E is not in C. I can fix it, but I won't. And C is closed under inversion. I can fix it, but I will. That's the joy of doing this. Wrong color, but what the hell. So we have that set. Then you get a K-graph. The vertex of the K-graph consists of the group G and two group elements are adjacent if this difference is in the connection set. Now you've got to be a little bit careful if the group's not commutative, but so you have to choose between right and left at various points if the group's not commutative. But the important thing is that if you do construct a K-graph, then the group you're using is indeed a subgroup of the automorphism group, as it should be. And in fact, it acts regularly on the vertices, which means that it's transitive. Given two vertices, there's an automorphism that takes one to the other. And the regularly says that given two vertices, there's exactly one automorphism. Okay? And so, K-graphs give you instruction where you have a known group acting in a nice way on the vertices of the graph. Okay. Now, the issue is that the automorphism group of the K-graph, well, it contains G, but it could be bigger. Okay, and so the question, and that's the next slide, is which groups have a subgroup connection set C such that the automorphism group of the K-graph is just a group you start with. Now, if you find such a group, they were called, I had nothing to do with this, they were called graphical regular representation, which was abbreviated to GRR. And now I'm not too fond of acronyms in general, but you really need something in this case. So that's the question. Now, there's an easy class of groups where this is going which won't give you GRRs. If there's an automorphism group that maps each element to its inverse, and it's not the identity, that gives you an automorphism which fixes the identity. And so the order of the automorphism group of the graph will be at least twice the size of the underlying group. Now, this is a fairly strong condition, and you can actually determine the groups that satisfy it. You get the abelian groups with exponent greater than 2. Okay, so if you have Z3 by Z3, you can take the map each element to its inverse. That's an automorphism, and it'll give the graph won't be a GRR. And there's also a class of things called generalized isocyclic groups, and we don't really need to. But basically, they're going to have an abelian subgroup of index 2, and they're a restricted family, and they emit automorphisms mapping a group elements to the inverses, so they can't work. Okay, so you've got an obvious class of things which are not going to have GRRs. Now, when you've done answered the obvious question, you can come back and say, well, how big can these groups be too? But I'm not going into that. Okay, so that was so our problem is, when this is true. Now, there was a lot of work done this by a number of people, and so I'm getting more of the summary. Initially they focused on solvable groups. Well, you want to, because they're easier to deal with. And a guy called Godsil in his diploma proved that if G is a finite solvable group and it's not abelian with exponent greater than 2 and it's not generalized isocyclic, okay, if it doesn't have a GRR, then the order group is in most 32 and it's one of 13 groups, sitting right down. Now, this particular thesis was sort of yay thick, and there was a lot of computation and a lot of cases in there, because basically you're trying to get together an induction proof. You're going to say, oh, this group's got a GRR in this group, and it's sitting in a subgroup in the bigger group, then I can get a GRR for the bigger group. Now, the trouble with inductive proofs, if you have a bunch of counterexamples at the base, your life gets more complicated, and then the more counterexamples, the more complicated your own can get, as you're all probably well aware. So, but Godsil did this, And so for my PhD, I worked on this, and I extended, well, I didn't have to worry about the solvable case. Actually, I proved this without reference I proved this twice. In one case, I used Hetzel's result. In this case, I didn't use Hetzel's result. So I proved you have a finite generated group, not necessarily finite, not a billion exponent greater than 2, and not generalized cyclic. And if it doesn't have a GRR, then it's got at most 32 elements. So so in a sense, Hetzel did the solvable groups, which is probably the hard case, and I worked through the not the rest of the groups. Now, the point I want to make here is how different things connected, because the proof wasn't entirely group, it wasn't just group theory. There was a graph theory involved too, and so as part of what I was doing, I essentially needed to work out what happened for groups generated by involutions. Now, I was interested in this because simple groups are generated by involutions. And so if I'm trying to extend Hetzel's result from non-solvable to general, I've got to construct GRRs for simple groups. So they ask the question now, so which simple groups, not a billion simple groups, will have GRRs? Well, I know that the group is generated by involutions. Can I come out and use that to construct the GRR? There is, and so again, the idea is induction. The idea is you start with a GRR for your group G and set C, and I want to add one extra element. So I get a new group generated by G and an element little h there, and little h squared is the identity. So I'm adding an involution. Okay. So the assumption is going to be that this group is generated by involutions, and I'm going to try and take the connection set for G, modify it a bit using H, and get a connection set which gives me a GRR for this. Now, this is a pretty crappy picture, but so the idea is we're looking at the group generated by G and little h. And we're going to just do the obvious. We'll take the connection set for G and now just throw in this element H. So the point about little h is it's not in G. And so when you look at the neighborhood of a vertex in this graph, it's going to be an isolated vertex. And it turns out if you can show that if you can show that any orbitals in the graph that fixes this, or maps this set to itself, then you're good to go. So how can I do that? Well, the easiest thing would be to assume, suppose that this vertex, this set here, which is giving the connection set in the Cuddy graph for G, suppose that connection set doesn't have any isolated vertices. Then there's no way this thing can get confused with that. Now there are some group theory details I'm glossing over, but it all works. So in that case, if this has no isolated vertices, then this construction takes a GRR for G and extends it to a GRR for H. So we're off on our induction. Well, that's all very good. What if, you don't have a lot of control about the GRR for G. And so, so what if it's not? Well, you do get connection sets in pairs. If you have the connection set C for the graph, then you've got the complement of C is the connection set for the complement of X. For the complement. And the nice thing is that a graph and its complement have the same automorphism group. One of the few times we get to say the groups are equal, not just isomorphic. Okay. So if my connection set that I chose for G doesn't work, I can replace it by the one for the complement. So if the connection set in the complementary connection set doesn't have isolated vertices, then I'm good to go. Okay, so now I'm left with the case that I've got a situation where actually I wrote not connected, I mean not bouncy, that if the graph and its complement, so if the vertex neighborhood in a transitive graph is complement and neither have isolated vertices, I proved by a graph theory argument that they had an automorphism of this form. And so that's an automorphism with, moves 4 vertices and fixes everything else in the graph. So it can't belong to the group G because the group G is acting regularly. So I don't have a GRR, so I can throw it away. Okay, so the point was that, if my connection set was bad and the complement was bad, I'm learning something about the structure of the graph. But the interesting thing about the structure of the graph that I had to use is that it was a 2 graph that Seidel worked on. Okay, and so related was people echoing lines things, these come up in that setting. And so what happened is that it turns out, and I knew this, well, I knew about two graphs because of the spectral things I'd been looking at. And so I recognized this problem that the graphs I was constructing were these two graphs, and then using this, I was able to take care of that. And so I got a complete characterization about when a group generated by involutions had a GRR. Okay. But the reason I'm going through this was the interesting thing that there was a connection with these two graphs, and there was no reason to look for it. It's just the way it just appeared. Now, actually, that paper I published was at least in part written when I was in the Open. I've got that picture there, which makes it look very attractive. It's Bill Fried on board. Okay. It looks nice from a reasonable distance. I think the universities are somewhere around here, but I can't quite work it out. Anyway, so that's I was in the Open for 2 years. And so I did work on a fair bit of work on Waterloo groups there. The other topic I worked on during my PhD was on graph spectra. Now, Brendan alluded to this and mentioned this earlier. And so this is basically a joint project, reflects things that Brendan and I were doing. It wasn't related to my PhD thesis, and it wasn't related to Brendan's PhD thesis. But we were doing it. And so I want to talk a bit about that now. I'm basically just going to list some of the things that we did. As Brendan said, we were constructing, we wanted to find examples of pairs of cospectral graphs. Because the standard thing, I can remember the graph theory course, and so Derek Holland's up there and says, this is the graph and this is the adjacency matrix. And if the graphs are isomorphic, then the adjacency matrix is a permutation equivalent. And we don't really know what happens in general. And Brendan and I are both interested in linear algebra, so we probably got interested in the obvious question that many people ask us, so when does the spectrum of the graph determine the graph? Okay, and there are a few papers and there's some examples. And in fact, you look at the small examples, and then you have a pair of examples, and the trick is to try and generalize the examples. And it turns out for the spectra, it can be surprisingly successful. That once you have one pair of examples, you can nearly always embed it, often embed it in an infinite family. And so we did that. Now, one of these, actually we'll do it here. This here's a pair of graphs. You notice that what's happened, I've basically taken the bipartite complement of these edges and got those edges. Modulo typos. Now, those two graphs are cospectral. Their complements are also cospectral. And this is something we noticed, that when we were finding cospectral graphs, it often turned out that the complements are also cospectral, and there's no simple reason why that should be true. Okay, it's not all. But so certainly for small graphs up to 10 or 11 vertices, if you're cospectral, then your complement's probably also cospectral. And so, but this is the smallest pair of graphs that are cospectral with cospectral complements. Now, the problem is you come up with something like this and you want to prove that these two things have the same spectrum. Well, that's easy enough. These are graphs on 7 vertices. This is isolated. This is just C6 and this is just a tree. So you can work them out, you get polynomials and everything's correct. Of course, it turns out you can generalize this and you can start gluing, copy of some graph here and then copy the same graph there. And they're still cospectral. We had programs which we let us prove that. Okay, but of course the problem then is, how do you actually prove that those two things are cospectral? You're not going to compute the characteristic polynomial, I don't think, because you've got some messy graph there on 15 vertices. So you got and not a graph on 19 vertices, and you're trying to work out the eigenvector. And so I was thinking about this, and it occurred to me, well, the obvious way to prove two things are cospectral is to find the orthogonal matrix which takes one to the other. And it turns out you can do that in this case. Very simple. So then it follows. So then you get this, and so this led to what's now called what I call local switching. So that was that was one of the spin-offs of this work about identifying cospectral graphs. We also got interested. Well, Brendan was sort of starting to think about these programs for graph isomorphism. So he was starting to think about that. And so in the course of our work here, we learned about equitable partitions. And if you're doing graph isomorphism, a lot of your time is spent computing equitable partitions. So Brendan and I did a lot of work on that. And so and Brendan used it extensively in both his master's thesis and his PhD thesis. The other thing project we got involved in was trying to construct the small vertex transit graphs. Now, I won't go into the details. It got to the point where, in a sense, I could do the graphs up to 12 vertices by hand, but Brendan wasn't very impressed with that. So he probably started writing programs, and these days they have up to 28 or 30 or something. It's not another story. But in the course of that, we end up we're looking for transit graphs. We end up working with what are now called walk regular graphs. So these are graphs where the powers of the adjacency matrix always have constant diagonal. And so we extended the feasibility conditions from distant regular graphs to walk regular graphs. And then Brendan used that in constructing trying to find exhaustively enumerate the vertex transit graphs up to a reasonable number of vertices. The other thing we did here was we came up with a proof that controllable graphs are vertically constructible. Now, controllable means that the adjacency matrix and the L1 matrix, the algebra they generate is the full matrix algebra. Now, that's somewhat surprising. The other point, this is a natural algebra to use because we're looking at automorphisms. Any orthogonal graph must commute with A and commute with J. And so it must commute with anything in that algebra. Okay. So, and so this algebra is the full matrix algebra. That's telling it the automorphism group is trivial. Okay, so, and so graphs said to be controllable. And I actually conjectured that almost all graphs are controllable, and that was proved by some people in control theory. They seem to got quite interested in the question. So there's we know that almost all graphs are controllable, and so that would give you a proof that almost all graphs are asymmetric. And so, but we, Brendan and I, well, this is the time where Tutt proved that if the irreducible polynomial of a graph, if the character polynomial of a graph is irreducible, then the graph is reconstructible. And okay, so irreducible polynomials are a bit of a pain to work with. And so the obvious question is, what if you just assume that the eigenvalues of the graph are simple? And Brendan and I tried to do it and didn't succeed. And then I remember Adrian Bondi was visiting Melbourne, and he said, and then Wilf announced that he had a proof for the simple eigenvalue case. So Brendan and I put it away. Then Adrian Bondi was visiting Melbourne. He said, no, there's a mistake in Wilf's proof. And Brendan and I looked at one another and we knew exactly where the mistakes would be. And so we came up with a proof of this. So that was somewhat interesting. So as I said, I worked on this spectral stuff with Brendan. The other topic I want to talk about is the matching polynomial. Now, this is this is quite early in my career. I was visiting Europe and I went visited Ivan Gutman in what was then Yugoslavia. And there was after that visit, there was a conference in Eger in Hungary. And so Gutman, I think, drove us up there. So we were all going in the same car. So we drove from, he's in Kragujevac in the south of Serbia, but we drove to this conference in Eger. And so we were talking mathematics on the way. And so he mentioned the matching polynomial. Now, he was basically a theoretical chemist. And so this will do for, so the definition of matching polynomial, well, the first you just say the number of k matchings in a graph. We're going to notify p of x comma k. And the matching polynomial is given by that mess there. So it's a generating function, if you like, or if you don't like to. So now the point that Gutman, well, this is the result of Gutman's that the graph is a forest if known the matching polynomial is equal to the character polynomial. So it's connected to the character polynomial, some fashion. Okay. Now Gutman said, he claimed that the eigenvalues of this polynomial, or the zeros of this polynomial, the zeros of this polynomial are real. And I didn't believe it. I mean, this formula, you can invent a somewhat more complicated expression here, and you can convert that expression into an expression of the character polynomial. So there is a connection. So the character polynomial, in a sense, involves not just matchings but cycles. And so, so you can sort of take the character polynomial, delete some stuff, and you get the matching polynomial. But there's no reason why that should preserve real eigenvalues or real zeros. So I said I didn't believe him. And well, as subtle as I am, and so then he said, "Well, no, I've done some tests on the computer." And I wasn't too impressed by that, because in those days when a graph theorist said, I've done some tests on the computer, they meant they'd done half a dozen. And I didn't think that would be enough for, small graphs at that. But he really came, he said, no, I've done hundreds. So I started thinking about it. At that point I said, okay, well, that's a different question altogether. And so I did come up with a proof. It was a bit of a lost cause, because we found out not too long later that there was a 60-page paper by Harman and Lee, basically on the matching polynomial, and they had 3 proofs in there that the zeros were real. Although I remember one surprising Goodman by saying there were 3 proofs, and he'd only found 2 at that point. So, which gives you some idea of what we're working with the paper was like. But so we proved that the zeros are real, and so we continue to work on that. And this is sort of the next sort of random connection. So if you use PM of X to note number of perfect matchings in your graph, then the following, some surprising formula holds: number of perfect matchings, the complement of X is given by this integral of the matching polynomial. Now, the interesting question is, why on earth would you come up with this? It actually also turns out to be useful, but it's not just a crazy identity. The simplest case is when you take the X to be the complete graph. So now you're looking at the number of perfect matchings in the, got something wrong there. Something crazy. Let me just go on and ignore it. That should just be the KN, I think. Okay. That's all it's saying. And you're using iPad. I didn't make a mistake, show me. So the number of perfect matchings in the complete graph is given by the double factorial. So it's n minus 2, n minus 4, and n has to be even. Okay. So the point is that there's an explicit combinatorial formula that gives you a number of perfect matchings in the complete graph. That's some sense of standard combinatorial exercise. Now, as happened, how did I see this connection? Well, actually, Brent and I were both TAing this basically tutorials on the algebra course. Not been really advanced, because they were doing Graham-Schmidt, and they wanted to use inner product that was more complicated than the dot product. And so one way of defining a nice inner product is to take a non-negative function f, and then compute and you have an integral product on polynomials. The inner product of p and q is integral of p times q times f dt. If that is not negative, then in general that gives you a valid inner product. And important inner products arise in that way, and you can then use that to give students some unexpected complications. Graham-Schmidt is bad in general. So the point was, in the assignment they were given this. They were told, okay, we're going to use the normal distribution. This is going to give us our inner product. For that, you need to know the moments of distribution, and there they are. And I thought, well, that's funny, because that's also this. And so I started thinking about that, and it turned out it's actually, in some sense, I'd already done the hard part. The proof that this works, the hard part is actually proving this. Because you've got to do an integration by parts. I don't know about you, but if I give you that and say integrate by parts, there's going to be some suffering involved. And the same for me then. And I haven't got any better. I never taught a calculus course. The point is the matching polynomial satisfies a number of recurrences, which are easy to prove, one of which is here. So I've got a graph X with an edge E joining vertices U and V. Then I'm going to say the matching polynomial of X is built from this X with the edge deleted, and this is X with the vertex deleted. And so the point out, and so now if I want to get the integral of some mesh times this, it's integral that mesh times this, minus integral that mesh times this, and you can use induction. And as I said, and that works. You have to think a little bit, but it's straightforward. As I said, the difficult part is the partial fractions. Okay. And so, yeah, so that was one advantage of TAing the algebra courses. I guess it's not directly right. As I said, the zeros of the matching polynomial are real, and Harman and Lee had 3 proofs, one of which was the first proof that I found. The second proof later on related to what I call the path tree. So we have given the graph X with the vertex V, the vertices of the path tree are the paths in the tree that start at the vertex V. So they're all open. And if they're to be adjacent, if one is the maximum subpath of the other, so you get it by adding one more edge. Okay, so that gives you a graph, and you can check that it's a tree. And once again, in a certain sense, again, it's fairly easy to prove by induction that you get the following formula: the ratio of these two polynomials is equal to the ratio of these two polynomials. This is getting close to what Gabriel was calling the neutrino identity, but this is essentially a generating function for the closed walks in the graph that started B. At the point about this was we've got the matching polynomial. We know the zeros are real. Now, if the characteristic polynomial you've got real zeros, there's also a bunch of other things. You've got the connection to walks and things. But this is indicating, in fact, well, this is the generating function for closed walks in the path tree that start with B. And so you're connecting these walks from this path tree. So you've got a class of walks that determine the matching polynomial in the same way that the closed walks determine the characteristic polynomial. Okay. And so to finish off, I found this in my files going through some. There's a picture of Dale Mesner as in Bose Mesner. Now, this is an AAS sectional meeting years ago. I don't have any pictures of Bose. They were both at Fort Collins, and well, just for your amusement. Aren't they cute? Okay, and so that's the end.
Thank you, Chris. Any questions? I have a question.
Yeah.
How are those, is it plovers that you call them, the birds? Plovers compared to the geese on campus here?
Well, the geese will come at you on the ground.
Oh, that's a difference.
And I found if you hiss back to the geese, they generally keep their distance.
Ah.
And they only come one at a time as a rule.
I had two
The
coming
plovers,
towards me
both
once.
parents would come.
Oh.
And so, you know, if you're watching them, you can't see them.
Nice.
Technically, they're not plovers, they're lapwings, but I don't think there's any bird watchers here, so.
Any other questions?
I'd like to ask Chris, what comes next?
This is turning a bit like one of my mother's questions. Well, I'm still working on the quantum walks and some related things. There's some other linear things I'd like to get back to, but for the moment, it's quantum walks. Right, so.
I'll ask a similar question. Is that okay?
Sure.
So, for a lot of us, our career path or the choice of research problems is affected quite a bit by who's in our department or who we ended up talking with, and I'm sure that there are different degrees to which your research direction was changed by people that you ended up working with. But can you give some examples of people who had the most influence on how things changed when you went to Leoben or to Simon Fraser or to Waterloo? Did things change because of the people around you?
For me, not so much. I'll make a general comment that if you don't have people to talk with about your work, you'll stop doing mathematics. You may think mathematics is something you do all the time, but it is a social thing. And if you don't have some, I mean, they don't. All you want is they should be prepared to sit there and listen and not laugh at you, so to speak. And then you have to turn the compliment course, so that you need that. Otherwise, you won't do it. So if you're in a situation where you've got no mathematician to talk with, and you find it's hard to do anything, well, it's not your fault. Now, yeah, I mean, these interactions, you know, I had interactions. I mean, I think I chose my own directions. I certainly, Wilfred Imrick, for example, you know, I had some important discussions with Wilfried, you know, that had a strong effect on what I did in my PhD thesis. And then I got interested in distributed graphs. Well, I mean, Brendan was more interested in distributed graphs. There was nobody else around interested in distributed graphs. And then I started doing that, and then I realized that most of the constructions and distributed graphs were using finite geometry, so then I started learning some finite geometry. And again, I was a long way away from any finite geometry. And so I think in my particular case, I tend to define my own problems. I mean, with the, I suppose, with the quantum computing type side of things, now you can blame that there was the Perimeter Institute, and as I said, they were throwing questions at me, and I realized almost immediately that I could do something to those problems, and I was just using the machinery that I'd used with working with Brandon. And so that was nice. And I also realized it was going to be a good area for students. Because you get students here at Waterloo, if they do this, they come out with a degree in, a degree from CNO, which is worth something, and in something graphical or combinatorics, but they've also got this training in quantum computing, and there are courses being offered, and there's a Perimeter Institute and IQC. So it seemed a very natural thing for the students to do. And so I fed it the students. Now some of my students were more stubborn, Max and Sabrina, and working on the problem through their PhD. But I mean, it was there, and it was and in that sense, it was a conscious decision. I mean, I had one course in physics as an undergraduate, and what I remember is the first lecture where he went in and wrote down the wave equation. Now we're straight out of high school. I wasn't even 17. You write down the wave equation, and there's these partial derivatives there. And, excuse me, we haven't done partial derivatives yet. We have done lot differentiation, but we haven't done partial derivatives. In response, well, they're just like derivatives. You just ignore the other variables. But yeah. So that's an answer of sorts, I guess.
I had a question about your GRR work, Chris. You mentioned that you did two proofs of one was about one used Hetzel's result and one didn't. So for the one that didn't, did you also take an inductive approach to the solvable groups?
Yeah, that proof is in my thesis. The other one, which is a normal length for thesis, the first proof was in the conference proceedings. Actually, a conference proceedings in EGA, and that's comparably short. So it was more work, but it was using similar techniques. And in fact, in some sense, I remember having a discussion with Wilfried, about that, and I realized that I could push it further. Now, I never published my thesis, so that's not true. I think Wilfried's got to publish. Does that answer the question?
Any other questions?
I forget, what was the condition when the matching polynomial is the characteristic polynomial?
If it's a forest.
And it looked like it was n-2r was the index for the.
Yeah, the reason that, it's not quite clear. History of matching polynomials is a little complicated. There's an Rook, there's early work on something called the Rook polynomial, which you can use the matching polynomial bipartite graph. And so the book by Riordan on combinatorial analysis has got some stuff on the Rook polynomial. Okay, the chemists, well, I think may have been the first to work. The chemists started working on the matching polynomial because it gave them information. I mean, you saw how chemists do things. You invent a parameter, and then you plot the parameter against the boiling point. And if the curve's straight, you've got a theorem. And I do complain about trying to talk mathematics to physics at some time, but the chemists are another world altogether. Yeah, so the chemists were interested. The point was that in a certain sense, the matching polynomial leaves out the cycle. And so the chemists were interested in things like called aromatic hydrocarbons, which are not like the alkanes that Boyan was talking about. These are basically planar graphs where the cycles are all 6 cycles. You don't want 4 cycles to be much stable. So benzene is the prototype example. And so the feeling was that in a sense the difference between the argument the zeros the matching polynomial and the zeros the ghost polynomial was a measure of the effect of cycles on property of the molecule. Now, you don't want to think too hard about what that sentence means, but that was their approach. And so because they wanted, so for the characteristic polynomial, the sum of the absolute values of the eigenvalues measure they viewed as a measure of energy. And so you could interpret the sum of the absolute values of the zeros and matching polynomials as a measure of energy. Now, that only makes sense if you know that those zeros are real. So that's why the chemistry.
So does it make it good sense why the characteristic polynomial will be odd or even?
Well, that's only true with bipolar graphs.
Oh, okay, that's,
Yeah.
now you get a question.
Well, that's all right. I got plenty of those too. Yeah, so yeah, I mean, the matching polynomial has got that symmetry property you just mentioned. And for the molecules that chemists are looking at, they tend to be bipartite because 6 cycles are stable. And this is why, chemists are very interested in that, why benzene is stable. But the 4 cycles, 5 cycles, are much other stable. So you see these pictures of steroids and Tino's got a Kathleen t-shirt and you tend not to see 4 cycles on the 5 cycles, but he didn't wear it.
Any other questions?
So when I came to Waterloo, you were working on a blue book, and then you went on sabbatical 1 year later, I mean, to Austria. So how is that blue book related to all the work? I mean, it is about this matching and
Well, I viewed it it was characterized by a matching polynomial and orthogonal polynomials. So that was the thing. And so, yeah, there's work in there which I haven't thrown at the student or discussed in this.
I remember that we had seminar with Norbert Seifter and Mark Yannickem, and you were talking about zonal polynomials at that time, but oh, this is really algebra.
No, it's not, it's analysis.
When's the continuous time quantum walk?
I know, so I was looking through my photos and I had a picture of the cover page of an old version of that, I think. That was 5 years ago. It's getting to the top of it's pretty close to the top of the list. Well, they've got a few things, for example, my real estate transfer paper hasn't been submitted anywhere yet. Nobody complained about that. We should knuckle down. I mean, the contents, getting the content organized is just the first 2/3 of the project. There are a lot of, as Harney can assure you, there's a lot of details to be taken care of once you submit the book, or once the publisher accepts the.
Any other questions?
So was Goodman closer than Seidel? I mean, to your work? I mean,
No, different. I mean, Seidel was, I forget how I first met Seidel. I mean, we were very, very interested in studying his papers. I mean, you got to remember this at this time, there's no internet. So if you want to know what's happening, then once a month, the latest copy of Math Reviews would arrive in the library, and you could rush in there and read what happened about a year and a half ago. And then you discover that in fact you couldn't understand 95% of the review because what slight idea what they were talking about. And then papers would cite unpublished lecture notes of somebody, and so the people were passing these lecture notes around. We're in Australia. So I guess that's in some sense why I got the habit of working a bit more independently, because but Seidel, I was interested in his work, and so Seidel was always very nice to people in general, and he gave me a lot of time. So
yeah, he left us that book with 100 papers or something like that.
Yeah. So, but he would talk at length. There are other mathematicians that weren't like that.
And then slowly BCN came out, and we were all working with copies of BCN.
We had spiral bound copies. Remember the blue cover and the spiral bound copies of BCN before it was published?
Yeah, my copies held together by duct tape. And I remember when Crystal Go went to left the university and she went to Vancouver to do SFU to do a PhD, and she was exulting. She could get the copy of BCN from the library. Nobody was going to recall it from her. The other thing I forgot to mention was that one reason I wanted to go to the GRS, when she went there, she went to, so she's in SFU starting on her work, and got some conversations with another graduate student, and he says, "Where are you from, Waterloo, and who are you working with?" And she said, "Me, oh, you must know about the GRR problem." And she started asking questions about that, and she didn't know anything about it because she was quite annoyed with me. As you might expect if you know Crystal.